that when I went to MIT as both an undergraduate and graduate student, my thesis advisor for my PhD was Amar Bose. And this event is in many ways a celebration of Amar Bose's passion and his inventive and innovative spirit. And this talk really reflects one of Amar's pet projects. Could you raise your hand if you have some kind of a direct tie to Amar from past experience? Okay, well we have a number, and we have a number, I hope the rest of you have at least certainly heard of him. Amar received his bachelor's and master's from MIT in 1951 and 52, and his master's was in the 6A co-op program, where you spend 6 months out working in an industry placement as well. And he received his PhD in 1956 under Norbert Wiener. Amar remained associated with MIT during the many years that he founded and headed the Bose Corporation. I'm sure that you've all heard of or used some of Amar's products. And in particular, he continued to teach his iconic and famous acoustics course, where acoustics was short for everything can be derived from basic principles. He taught that even as he was taking almost weekly trips to Europe as part of the young Bose Corporation's struggle to expand to a worldwide marketplace. Amar was still relatively young when I arrived at MIT, but he was already legendary for his lucid and insightful approach to circuit theory, acoustics, and system thinking. As I mentioned, I did my PhD under him. His focus and integrity were like a fundamental force of nature. And like many others, I absorbed from his passion and commitment in actually becoming who I am, and I had that serve me throughout my career. I hope all of you, young, medium, or old in your careers, grow to develop, learn, and apply that same type of curiosity, passion, commitment, and a determination to make things work. The talk is sponsored by the GEL, Gordon Engineering Leadership, and UPOP undergraduate practice opportunity programs, which help develop the character, teamwork, and leadership skills of undergraduates in the MIT School of Engineering, and also by the Super Europe program, which gives engineering undergraduates an opportunity to engage in meaningful and hands-on projects. They have a great impact on our undergraduates, and I think Amar would have strongly appreciated them. And finally, this event is meant to reintroduce to MIT one of Amar's students, Neil Latritz, who received his bachelor's and master's and spent some years working toward a PhD at MIT as Amar's student before going to Bose Corporation to work for Amar, including being chief engineer for the landmark Bose automotive suspension system and having the high distinction of teaching Amar's courses within Bose. I'm delighted that Neil will be speaking today, and as I said, it's about one of Amar's many obsessions, which I have retitled as How to Design an Automobile That Flies by Using Loudspeakers to Drive the Suspension. Thank you.
Quick thank you. Putting a talk together like this involves the work and coordination of a lot of folks. So again, I want to just acknowledge Joel, the team with GEL and UPOP. And for those of you who aren't familiar with GEL, one of the things that I was always really fortunate at Bose and in all of my subsequent roles, I've always been involved with recruiting, coming on campus and talking to students. And I will tell you that students who participate in those types of programs, those leadership programs, are notably folks that always sort of stand out in a unique way that as a person in industry we would always aggressively go after. So I just want to put a plug out there. If you're thinking or considering, or you know people who are thinking or considering those programs, I can't encourage them enough. They're really terrific programs in terms of getting some industry experience. And as Joel mentioned, that was something that Dr. Bose himself was always really passionate about, was getting more industry experience into the university. That's kind of why I wanted to come and share this. So I'm pretty fortunate because I get to spend about the next hour or so sharing with you probably the most interesting and challenging technical problem on which I ever got to work, which is this suspension project. And I want to start off with one other little disclaimer, which is any really interesting technical project is always a result, at least in my experience, of a team of incredibly talented folks. So many people worked on this technology for a lot of years. Some of them are actually in the room right now. So I just want to be clear, I'm just the lucky guy who gets to stand up and share a little bit about it. So let's dive in. So take a look at that picture. And if you see top car going over some bumps, bottom car going over the exact same bumps. Bose Corporation. I mean, when you think Bose Corporation, the first thing that jumped into your mind was, hey, they're going to be working on an automotive suspension system, right? Right? I mean, it's totally logical. So there's two things I want to accomplish during this talk. The first is I want to make sure you understand technically what we were able to achieve. And I will tell you what our goal was. The vision that we had in our head was that we wanted to build a car that as it drove down a bumpy road would fly over it. Literally, it would be like Aladdin on his magic carpet, riding over the bumps, not feeling anything. Now, the reality, of course, isn't that pure, but that was the goal. The second question I want to answer, and where I want to start, is why on earth would Bose Corporation be involved with that? Involved with suspension. And to be really clear, this is the Bose Corporation that you've heard of with headsets. All right. Those of you, many of you probably didn't get a chance to ever know Dr. Bose. He was a professor here, as Joel mentioned, for 45 years, taught introductory network theory and then acoustics. And as Joel mentioned, I had this opportunity to take the acoustics class from him. And sure, there was some theoretical acoustics, but the light bulb moment for me was what Dr. Bose was really interested in is that as an engineer, you're often trained in a particular discipline. So maybe you think of yourself as an electrical engineer or a mechanical engineer. And what he would try to convey to students, and that's what I want to really talk about today, is that all of the different fields of engineering are linked by the common language of mathematics. All right? They didn't tell you this in 1803 when you took it. All right? But differential equations are actually helpful. All right? And if you understand them in one discipline, you can use that in all of the different disciplines to solve different engineering problems. So just to put it in perspective, Dr. Bose's original research at MIT was in transistors. Transistor was a brand new device. He was interested in building switching amplifiers and figuring out how you could deliver power using those devices. Right? When Bose Corporation itself was formed, it was formed as a switching amplifier company. That was its first products. A couple of years later, some acoustic products came out, and those took off, and that's the reason people tend to know Bose as an audio company. But Dr. Bose's interests were always much, much broader. So let me sort of give you a sense of what I mean by this cross-disciplinary sort of point of view. So do just a little bit of math here. All right? I'm going to keep this dead simple, but over on the left, capacitor. Right? Freshman physics, you learn I is equal to C dV dt. So there's a relation between current and voltage. Right? So that's an electrical device. All right. By the way, I'm going to write one true whole version of engineering. Yeah, there's these, but there's a dating process. So over on the right is a mechanical device, a mass. All right. It's pretty fancy. All right. It's governed by Newton's law, F equals ma. Now, this is the point where I'm going to do something completely and utterly unmotivated, okay, for no apparent reason. And this is sort of classic MIT lecture style, right? For no apparent reason, the professor would do some substitution of variables, right? As if they knew, like tablets on high, they had seen something. It's like, oh, just do this substitution, it'll all work out. Okay, we're going to do a substitution of variables, and instead of writing it as acceleration, we'll say acceleration is the time derivative of velocity. Right? And now, if you squint and you look at those two equations, you can go, they're kind of similar, right? If I look at current as a force and voltage as a velocity, and heck, they even start with the same letter, so that's good. They sort of look like the same equation, all right? It's an obscene coincidence. Let's move on, right? So let's try it again. So over on the left, I have an inductor. Again, freshman physics, you learn V equals L di dt, so there's a relationship between voltage and current. All right, terrific. Let's go over to the right.
Now I'll notice, and this, again, I have to point out, the mechanical engineers steal the electrical engineering symbol, right? They put us, that's a spring. And you have Hooke's law, so F equals Kx. And again, unmotivated, divide both, I'll write that as X equals 1 over K times F. For those of you who aren't familiar, 1 over K is typically called the compliance of a spring. It's typically denoted with a C. That's annoying, because that's what capacitors are denoted with. Okay? So I've written 1 over K here just so it's not confusing. All right? But it's just this thing called compliance. And if you prefer your mechanical engineer, just throw a C up there and life is good. All right? And then again, substitution of variables. What I'll do is I'll take the derivative of both sides of the equation. I get velocity equals 1 over K df dt. And again, let's squint at that equation and you go, wow, there's something similar between a spring and an inductor. Good thing we use the same symbol for those things, right? And for me, this was a light bulb moment. All right, when Dr. Bose started introducing this in the acoustics class, it was this opportunity to sort of say, wow, I was trained as an electrical engineer, and I start to actually know something about mechanics. And let me take this even a little bit further. Again, freshman physics, you learn Kirchhoff's current law, Kirchhoff's voltage law. Like Kirchhoff's voltage law says that some of the voltages around a loop are always 0. You add up all the voltage drops, you get back to the same original point. It turns out there's an equivalent statement around velocities. You have a mechanical circuit with a whole bunch of springs and masses all tied together, and you go around the loop, the sum of the velocity drops, or if you will, the sum of the velocities around that loop, 0. So there's an analogy between KVL, Kirchhoff's voltage law, and if you will, Kirchhoff's velocity law. No one would ever call it that. And similarly, Kirchhoff's current law says the sum of all the currents into a node must be 0. First thing mechanical engineers learn is to do force diagrams, and they learn that the sum of all the forces into a node has got to be 0. Right? If not, if the node had any mass, it would shoot off to infinity. So sum of the forces into a node has to be 0. There's an analogy there. So what can you do with it? So let's start with a mass spring example. All right? I know it feels like 802. I appreciate that. Look at that. So on the right-hand side, you've got a spring mass system. Right? Now, if I were to attack this, what I would normally have started doing is writing differential equations. And I would have beaten on it for a while, and I probably at the end of the day would have figured out, oh yeah, there's a resonance square root of K over M or something like that. Would be the frequency. And I could probably even start to write the equations that said, if I were to take the spring up on top, and I was the source with my hand, and I had a spring here and then a mass, at low frequencies, the spring and the mass would move mostly together. I'd get to that square root of K over M frequency, and I don't know if I can do this, I'm not a good drummer. This would be moving a whole lot, this wouldn't be moving very much. And then above the resonant frequency, they actually move in opposition to each other. Right? And I could do all that math, and I could probably figure it out. Maybe I wouldn't make too many algebraic errors in doing all of that work. But we said a spring is just like an inductor. So if I have a spring, the spring constant K, if I make it as an inductor, 1 over K, and then a mass of mass M, all I have to do is put together a capacitor of size M, and I've got an LC circuit. So the circuit on the left, so for instance, if I had a 2 kilogram mass, I'd use a 2 farad capacitor. Sure, it's a little hard to find that in the lab, but I can still make SPICE run that simulation for me, right? And whatever the compliance is in so many newtons per meter, I just invert that and put in an inductor of that many henries. And there's a one-for-one correspondence. The differential equations that govern the circuit on the left are exactly the same as the differential equations that govern that mass spring system. So what does this mean? It means, as, for instance, an electrical engineer, I've been taught all of these different techniques for solving LC circuits. You can do transfer functions, right? Which is basically using Laplace transforms to replace differential equations with algebra, right? So if you've been exposed to that, you know, oh, you look at that, the circuit on the left, you know, it's a second order low pass filter. All right? At low frequencies, I can talk about the transfer function from source velocity to the velocity of the mass. At low frequencies, they're going to move together. At resonance, which is 1 over square root of LC, right? What you get is, again, square root of K over M. And you'll go through 180 degrees of phase, And then you'll get to at high frequencies where this is rolling off as a second order system. Right? And what's interesting about this is you can use these same modeling techniques to work in the area of acoustics, thermal. It branches across almost every field that I've been exposed to, including, for instance, computation. So one of the things that's really powerful about this is I want each of you to start thinking yourself not as I'm trained in a particular engineering discipline, but the tools you have you can apply anywhere you like. So let's go into a particular example. Actually, I'm going to do one more thing. You can expand this even further. A lot of mathematical work was done in the early 1930s on LC ladders. All right, so this is an LC ladder. And if I take each inductor and each capacitor, and I write them cleverly so that they are the form of, they have some distance associated with delta x, and I take a limit as that goes to 0, and I increase the number of elements to infinity, believe it or not, this approximates a transmission line. Okay? So some of you took, let's say, electromagnetics, and you studied electromagnetic waveguides. You didn't need to. All you needed to do is use a whole lot of LC circuits. All right? And in fact, acoustic waveguides, and these are the appropriate equations for an acoustic waveguide, are governed by basically an infinite stream of these. And it kind of makes sense, which is that the capacitors in this equation are governed by the mass of air. So if I go off and I get a box of air that's a meter by a meter by a meter, all right, it weighs about 1.2 kilograms. That's the density of air. All right? So, and I've got to get the units just right, but if I take that density, rho naught, multiply by delta x, and I call that the mass in this ladder, and then similarly I set up an inductor. Now here the inductor is meant to represent the compliance of air. All right? So what I want you to do right now is imagine that between my mouth and your ears, there's a string of air particles. So this is a one-dimensional problem. So if you will, there's a little particle of air, imagine a little sack of air in here. Then next to it, next to it, next to it, next to it, all the way to your ear. So as I'm talking, all I'm doing is shaking particles of air. Right? And that just goes down the chain. That air has mass to it, but it also has some compliance to it. All right? Where do I get the compliance? The gas law. All right? So most of you are familiar probably with the isothermal gas law, which is PV equals a constant, P equals nRT. For acoustics, you deal with compression. Well, the isothermal gas law by definition says that there's no temperature change, which means that it happens slowly. There's time for thermal diffusion. In acoustics, you're dealing with vibrations between 20 hertz, let's say, and 15,000 hertz, or 20,000 hertz kind of numbers. So what you've got is a situation where you're compressing air so rapidly there isn't a thermal diffusion time. So you use the adiabatic gas law. Just out of curiosity, how many of you have ever studied the adiabatic gas law? I'm not sure if it's ever taught anymore. So that's basically PV to a gamma as a constant. All right? If you then sort of look at that pressure-volume relationship of that air particle, and you linearize it around atmospheric pressure, you get a spring constant of gamma P naught. Okay, that's the way the math works out. So suddenly, you've got a spring of gamma P naught, or 1 over gamma P naught. You've got a mass that depends on rho naught. And if I assemble an infinite tube of those, I get an acoustic transmission. Now at this point, you should be just about falling asleep. Okay? So again, why might you care? This stuff actually has a real purpose. So let's use a simple example. Up on top are 2 Bose products that came out in the 1980s. They were based upon waveguides. What I was trying to solve is, you guys hear my hand moving air? Really loud, isn't it? Right? Why can't you hear it? This is the interactive part. There was a quiz. Really? Why can't you hear this? Okay, it's too low. Great. I'm now moving it 20 times per second. Got louder, right? I can't actually move my hand 20 times per second. I admit that. But if I had a speaker right here and I held it up and I was playing it back and forth, driving it 20 times a second, it'd be wildly loud, wouldn't it? Right? So why can't you hear this? What's going on?
The energy is getting dissipated into a very big volume instead of being channeled twice.
Okay. It's close, not quite accurate. What's actually going on is that the sound, if you will, the air pressure that I generate on the front, speed of sound is such that it has plenty of time to run around to the back, and I generate no net pressure. So the way you make speakers make noise is you put them in boxes. So in other words, if I took this driver and I put it in a box, and now I move it back and forth, the sound can't get around the back, and you have no canceling of the pressure, so now the energy has to radiate out. All right? So fundamentally, if you're in the business of making speakers, and good, I will hint, Bose Corporation is, all right, you gotta make boxes. All right? Any of you who have ever tried to make a box knows that it is surprisingly difficult. You have to get it sealed. It can't have a leak. And making sealed boxes is tough. And this was a bit of a problem in that Dr. Bose heard about. So he was trying to figure out, how do I get around this? So the first part of the idea was, oh, okay, well look, if I take a speaker and I connect it to a tube, with a pipe organ, right? I mean, you guys have all seen pipe organs. You have a tube, you put a speaker in front of it, great. Kind of works. The clever idea he had, which is up on the left, upper left of that picture, is if you also put a waveguide on the back, you get two pipe organs, they can cooperate with each other, and they can essentially play broadband noise. All right? So the device up on the left is called the acoustic wave cannon. I'm not making this up. It was literally 12 feet long. Okay? It was 12 inches in diameter. All right? It would hang in electric ball. Okay? There were a bunch in 10250 for a while. I'm sorry, 26100 actually. I don't think they're there anymore, is my guess. At one point, I had one in my dorm room. Very impressive low frequency response in the dorm room. So this device actually went down to about 27 hertz and could reproduce and generate significant sound pressure. So the company started making this, and they started making variations of it. It turns out you can fold up the waveguide to get the device that's up on the right, which is called the acoustic wave system. And then there were variations of that, the wave radio and a variety of products that Bose Corporation came out with over the years. But here's the really interesting thing. That waveguide, you can model as a whole bunch of LCs from the previous slide. So if you go back to this, those waveguides, you could write out the transmission line equations, or you could approximate it with this in, for instance, a circuit simulator. If you take a couple of LCs and put those together, you can sort of say, that kind of approximates a really good waveguide. You can then back synthesize the acoustic circuit that makes that. And with acoustics, the elements you use are tubes, which are masses of air, and volumes. All right? The best example you would probably see is blowing over the top of a bottle. You have a tube and a volume of air. It's a resonator. Right? And it makes a note when you play, when you blow over the lip of the bottle. So the device on the bottom, which is called the Acoustimass base module, is a low-frequency approximation to a waveguide. Right? So if you understand this stuff, you can be pretty inventive. You can make all sorts of crazy things. Okay, so let's get to the craziest of the ones that I know about. Making the car fly. That is literal. That's a picture of the car jumping over a 2x4. All right? If there is ever an Olympic event for a vehicle steeplechase, this car should win. All right? So let's talk about how that came to be. And again, I want to go back to a modeling-based perspective. So the first thing I want to do is I want to make a simple vehicle model. So what's typically done is a vehicle typically has 4 wheels. So what I want to do is 4 wheels is a little bit complicated. So let's simplify that. So the first thing we're going to do is cut the car in half. All right, so now I've just got the front of the car. It's got 2 wheels. Still too complicated. I'm going to cut it down the middle now. And I've got 1/4 of a car, a quarter car. All right? That's what's shown on the left, a quarter car model. The other thing is I'm going to make another simplification. I'm only going to consider vertical input at this point. I'm going to ignore anything in the forward or after lateral directions. And the reason I'm going to do that is because I'd like to get some insight into how this thing is going to behave. And here's the next trick about models. At every point in my career, every time I have ever made a model, I've simultaneously wanted to do 2 things with it. One is I wanted to make it more complicated, to get more accuracy. So I just made a pretty simple model of a car. But you can always make it more complicated. And that's really helpful when you go after computational techniques and you're trying to optimize your system in some way. But the other thing I've always wanted from the models is for the model to be simpler. I am not that smart. Okay? And my goal in life is to figure out how to make things as simple as possible so I can get some insight. All right? So this quarter car model is a relatively simple model. And you can actually make it even simpler. But this is where we're going to start. So over on the left, just to be really clear, what we've got is the wheel. Typically, the moving mass of a wheel is on the order of about 50 kilograms. So if you take a wheel out, you weigh it, and then you throw in the brakes, the rotors, the suspension links, and all those bits and bobs, you get somewhere around 50 kilograms. All right? And it turns out tires also have a compliance to them. Now here I've actually put C here where I'm referring to compliance. This is 1 over K. So it's 1 over the spring rate of the tire. Those of you who haven't had a chance, if you go get a tire, you can actually bounce it like a basketball. It has some pretty good compliance to it. The resonance of that mass spring system of just the tire is around 12 or 13 hertz. How do I know this? Because I've driven down the mass pike before with an unbalanced wheel. Okay? When you're driving down the mass pike at about, say 55, 60 miles an hour, the wheel's going around about 12, 13 times a second. If your wheel's not balanced, you'll feel that shimmy in the steering wheel. That's vertical input that's coming from your unbalanced tire. What's the solution? It's a second order low pass filter. You want to get rid of it? Drive faster. It'll roll off second order. These are important tips. Okay. So you've got the mass of the wheel, the compliance of the wheel, and then that attaches up to the car body. The car body we're going to call simple mass. Okay, and you're sitting up in the car body. And it connects with, you've got a suspension element that is a spring, so it has some compliance to it, and a shock absorber, or a damper unit, a mechanical damper. All right? The spring mass system, the suspension spring mass of the car, that typically resonates at about 1 hertz. Suspension springs are typically very soft. So here's your homework. Go out to the parking lot tonight, walk up to any random car, and you can push it down. You'll notice it's only a few newtons to get displacement. You don't have to push very hard. These are softly sprung cars. All right? Pick your own car if you can. And then there's that shock absorber. We'll talk a little bit more about it. So here we go. We have the variables I'm going to pay attention to is the displacement of the road, and I can take all the derivatives, and I've done that over on the right. The velocity of the road, the velocity of the wheel, and the velocity of the car. And I'm interested in how much does the car body move. I'm not a mechanical engineer. I can't understand the thing on the left. But the thing on the right, that makes a lot more sense. That's a circuit. So on the right is an electrical circuit that's a 1-for-1 equivalent to the behavior of the mechanical system. Right? You've got the compliance and mass of the wheel, and so on. And what's nice about this is now I can use all the tools that I've been trained with to figure out transfer functions, behaviors, and make predictions about what's going to happen. So, if I move forward, and I lost my little pointer, right there. Thank you. I'll end it with these graphs. So, the green curve is the transfer function from road to wheel. So this is a second order system. This is about 10 hertz, so that's around 12, 13 hertz. And you'll see, yeah, rolls off second order. So this is what I was saying, if you drive faster, you'll get less vibration into your car. All right, it's a good move. The red curve is the transfer function if you have wheel motion to the car, but let's look at the blue curve, which is the overall net result. You'll notice that as you drive down the road, there's a resonance where the car is exacerbating motion at around 0.9 to 0.8 hertz in this particular example. But then it starts rolling off, and it would be great if this started rolling off second order, but it doesn't. It rolls off only first order because of that stupid shock absorber. All right? So if we could throw away the shock absorber, we'd instantly get better performance. Okay? Sure, there'd be one little nasty side effect, which is that's the only thing that's damping this resonance and damping this resonance, so those would go off to infinity, but that's just a rounding error, okay? We'll ignore that. So this rolls off first order, eventually the tire kicks in and we start rolling off third order. So that's the frequency response of a normal car. All right? I put this up because I want to then show you what the idea that Dr. Bose had was. I've given you all the same information he started with. I had the opportunity over the last couple of years to go through his lab notebooks and sort of see how he came up with the ideas that he came up with. He's a pretty inventive guy. All right? And what I'm telling you is you're staring at everything he knew about cars at the time relative to suspension performance. So how would you make it better? Well, I'll show you what he did. He said, I'm going to replace the thing between the wheel and the car with an ideal force source. That's it. That's the idea. Okay, I'm done now. That was the idea. And so to be really clear, how would you do? What would you do at this point? Well, you can look at the circuit or you can look at either side. If I now run a servo system, and I say, I'm going to allow no force to get into the car body, I can build a car that as I drive down the road, the mass of the car doesn't move. Right? So if you will, I just need to set up a servo system so that the force, the current that gets into that capacitor, or the force that gets into that mass, and those are equivalent statements, is zero. That's it. We're done. All right? So that was the initial idea. Just replace the suspension elements with an ideal force source. All right? That was sort of the original idea. Now, this is the part where, if it was a Hollywood movie, I tell the story a little different. I could tell you the truth, by the way. Actually, what if you were the truth of a Hollywood movie version of this? I can leave. I guess I'll tell you the truth. Okay? That original idea sort of happened in around 1980. Okay? Just out of curiosity, show of hands. How many of you were alive in 1980? This was a long time ago. That's my point. Okay? That was Dr. Bose's original idea in 1980. Okay, so what happened next? Well, the next thing they needed to do is they said, oh, this is great. All we have to do is figure out how to build a servo system for driving down real, honest-to-God roads. Now, here's the thing. In a vehicle, you have a certain amount of suspension travel. A typical sedan will have on the order of 200 millimeters of suspension travel. Now, that's a pretty typical number, so about a little over 8 inches. All right, sometimes you have a little bit more, sometimes a little bit less. But in order of magnitude, that's what most cars have. Now, in most servo systems, when you build them, the rule of thumb is make the disturbances really small so you don't use up much of your actuator's performance. Either its force capability or its travel. Right? That sort of controls 101. Right? Don't push the actuator too hard. The problem is there is no road out there that is flat to within plus or minus 200 millimeters. Okay? I defy you to find anything in Cambridge, for instance, that is that flat. Okay? You've never even seen a pothole that's that shallow. Okay? Right? You're constantly dealing with running out of travel. So the next 4 or 5 years, we're focused on making a control system that instead of was always running in what was called a linear region, was constantly going into the nonlinear region. You're constantly hitting the stops. Right. So that was the work, is how do you figure out a good control system? Now, out of curiosity, how many of you have taken control of this sort? Fantastic. What's the first thing you do? You get a cost function. And then you optimize the cost function, and man, we are done. Finished. Okay? So why did it take these guys 4 years? There's no cost function. The measure of success is that a person is happy. So we need a smile meter. Okay? Now, I'll be honest, every single engineer I ever knew who started working on this suspension project would come forward and say, all I have to do is make a comfort meter and I can solve this. This is going to be great. I can write a closed-form solution for the controller for the suspension system. I will tell you, I know of many active suspension projects going on in the industry today. Every single one of them that I know of has started with, let me come up with a comfort function. All right? Most people go after acceleration of the person, maybe the first derivative of acceleration, which is called jerk. Why? It's called jerk. Or the second derivative of acceleration, and they try to minimize that. All right? I've yet to see a successful cost function for this. All right? So that was sort of problem one. Now there's a second problem with this particular design. That ideal force source, I gotta go find one. Okay? So you have to find an ideal force source. Now we have a model, and the cool thing about models is you can do all sorts of simulations. So the first thing is, do you need a really ideal force source? Can you use a crummy force source? I'll give you an example of a crummy force source, a resistor. Okay? Force and velocity are linearly related. Is that good enough? All right? It's an example of something that generates force. I'll even make it a variable shock absorber. Okay, a variable there. Right? Because those exist now too. The problem you get to is, imagine I'm driving down a road. I'm the car body and my hands are the wheels. All right? And I go into a corner. Well, in a typical car, the car will do this as I'm turning that way, right? So I generate motion, the car rolls. A shock absorber can generate force only in opposition to motion. You need force. The force is only a result of motion. So if you want to keep the car body flat through a corner, you've got to be able to put out force with no relative velocity. So fundamentally, you can't use a device that can only absorb energy. You have to be able to generate energy. So passive shock absorbers don't meet the performance target that we have. Now let me be clear, that doesn't mean you can't build a nice suspension with those. We weren't looking at that for our particular targets. So then the next idea was go and look at things like hydraulics. Hydraulics are great because they can generate forces. And again, you can throw that into a model and start to go, is it good enough? The problem we had with hydraulics, just to be really clear, is as you're driving down a road, let's suppose you're going really slowly, something like 30 miles an hour, about 45 kilometers an hour. That means in 1 second you traverse about 10 meters. A typical pothole, maybe it's half a meter across, so you're through it in a 20th of a second. Those are audio frequencies. So you've got a problem in that. Hydraulics, moving fluid, you've got inertia, it's hard to get it to move that fast. So we had to come up with something else. And I'll show you what was actually created. And I will point out one of the inventors just walked into the room, sitting over in the corner quietly, so I will embarrass him in public. But Bob is one of the inventors for that. That device, just to be really clear, what that is up on the top sits in the wheel well. And this piece down here attaches to the wheel. And it's a linear motor. Has about 200 millimeters of travel. That's good, that's what you need. This particular device was capable of putting out over 7,000 newtons of force at 5 meters per second. Okay, so if you sort of do the math and you work that out, yep, it can reproduce audio. Okay, so yes, it was a really tremendous audio. Okay, and yes, we were able to play music through the car back. Okay, and I have some clever videos of doing that. If we had one of these under your seat right now, we could launch you through the ceiling. All right, got to be able to move the car. So this was our approximation to an ideal force source. What it is basically magnets up the middle, coils of wire on either side. So if you want to make this thing work, then the only other piece of the puzzle that you need is you need a power amplifier. You have to deliver some power. So built into that device is a 30,000 watt switching amplifier. That's a 30,000 watt amplifier. There are 4 of them in a car. That's 120,000 watts. Okay, that's about 140 horsepower. Okay, typical car has maybe 200 horsepower, maybe 250 horsepower. So we only needed 140 of that to go, right? Right? Not going to work out so well. But here's the cool thing about electromagnetics in general, is as you're driving down a bumpy road, when you get to the pothole, you have to push the wheel into the pothole to keep the net force on the car body zero. Okay, that's the job of the servo system. So power flows from a storage system, battery typically, through the switching amplifier, pushes the wheel into the pothole. Tremendous. All right, you just spent 30,000 watts. But on the far side, motors are generators. The road now pushes the wheel up. The motor acts as a generator. The power amplifier is bidirectional. It recovers the power. All right? For instance, you probably know in every hybrid electric vehicle that's out on the road right now, there's something called regenerative braking. You step on the brake, the battery charges. That's what this was doing on a pothole by pothole basis. Okay? Every time you went over a pothole, power would flow out, most of the power would come back. So the net power efficiency of the whole system was under about a kilowatt per typical day. And a kilowatt, just to put that in perspective, that's roughly about, and your air conditioning system uses about 2 or 3 times that. All right, so it was a fairly small load on the engine. So all we needed was that ideal force source, and then the next step is bolt it into a car. All right. There's another 15 or so years of history that I'm going to skip over at this point, okay? And sort of say the bolting into the car part was a little less clear than we thought when we started, okay? And again, I want to talk a little bit about the modeling aspect of this from the systems perspective. Is that, again, if I'm the car body and you're driving down a road, in a normal car, you know, you're rolling and pitching and doing all sorts of things. And if you want to maximize the tire contact patch, think about that. If the car rolls, you'd like the wheels to stay perpendicular to the road.